Nguyen, and today I will be presenting our work on authoring system for genomics data visualization. We are a team of researchers from Department of Biomedical Informatics, Harvard Medical School in Boston in the United States. So the motivation of our work comes from genomics visualization authoring, which often involves human input and decision making. First, previously we did an interview workflows with genomics experts to understand the visualization authoring workflow with genomics data. And authoring is the process of transforming data into visual representations. And our interviewees were biologists, computational biologists, bioinformaticians, and software engineers, among others. And here is what we learned. Much of authoring is about starting with an existing example and modifying it. For example, a step-by-step. First, we would search online, let's say Google or Stack Overflow for visualization examples. Then we copy an existing code example and we edit the examples to fit our own data and needs to create a visualization. However, for genomic visualization, there are far fewer examples available online. Therefore, the researchers must often build from scratch or devote extra time searching. And this entire process is very time-consuming and inefficient. That leads us to our two key questions. First, where can we get a collection of genomics visualization examples? And secondly, how do we effectively query that collection and find relevant examples? That leads us to our goal to build a system that can enable efficient retrieval of interactive genomics visualizations and then serving as adaptable templates for authoring. Our solution is to build a multimodal search and authoring system. Before moving on to our methodology, I wanted to quickly mention the background on Gosling grammar. So Gosling is a declarative grammar for genomics visualization, specialized for genomics data. Gosling provides features for visualizing genomic coordinates, multi-scale navigation, multi-track layout, and interactive exploration. As you can see on the big figure, on the left is the Gosling specification, and on the right is the corresponding visualization of mark displacement. Next, let's take a look at the methodology. I wanted to present Geranium, genomics visualization retrieval for authoring with multimodality. This workflow starts with input query. The users begin by submitting a unimodal query in one of the three formats: image, text, or specification. And then we have the module of document collection, where each document is represented by a triplet of three modalities: image, text, and specification. Here's in more detail. To collect data, we start with Gosling spec here, gathered from application from public examples and real-world examples. We built the corresponding image and description for each visualization, with an example can be seen on the right. We have the spec, the image, and the corresponding text. We ended up with around 3,200 examples from around 50 different categories for genomics visualization. That is the module for document collection. Next, we have multimodal representation. This is where we transform the raw data from each modality into the embeddings using specialized transformation functions. Here we have different strategies for creating embeddings from raw data for each modality. The approaches are: first, we have context-free grammar encoding being applied to only specification. And this approach is stemmed from grammar variational autoencoder. We have two different smaller strategies, which are one-hot encoding and frequency count. Next, we have a fine-tuned text embedding model being applied to specification and text. Lastly, we have BioMedClip multimodal encoder, which is a foundational biomedical images vision language model. and being applied to all three modalities. So that is the second block of multimodal representation. Next, we have multimodal retrieval. This is where we compute the similarity between the query and the document embedding to output a ranked list of relevant visualization triplets. In this table, we show the modality pairings for query and document. So for query, we can see there are three big rows for specification, text, and image. And at the same time, we have three corresponding modalities for the output document, also specification, text, and image. In here, we can use different strategies for using different combination of query modality and document modality. Here is the retrieval result with top K accuracy per modality. So in here, our metric top K accuracy tells you if the correct answer was among the model's top K guesses. And from our observation, we saw that first, within modality searches exhibit the highest accuracies across all modalities. For example, spec to spec, image to image. And then frequency count shows promising results and is not computationally heavy. Last but not least, we have the authoring module, where we select the retrieved results and directly editing and specifications, any specifications as scaffolds for starting point. And after here, I will play a little demo to show the prototype that we have built. First, let's search with the images of single view bar chart. As you can see on the right, we have the list of retrieval results. Each result is a triplet of image, text, and specification. With a specification, you can directly open this code and directly modify it in the editor. You can also interact with this visualization as well. Let's do another example of multiple view. In here, we have a multiple view of a linear layout and a circular layout. On the right, we have a list of results that are multiple view visualization with different compositions. Let's try to search with text. First, let's do a general visualization type, for example, circular layout. Here, the genomic coordinates is along a circular layout. Next, we can search with something more specific, for example, comparative matrices with high-C and micro-C datasets. And on the right are the retrieval results with the comparative matrices. You can directly open an editor and interact with the visualization with the interactivities like zooming, panning. And last but not least, let's search with specification. This is an entire full spec, and here's how the visualization from this spec will look like, a stratified bar chart. Besides the full specs, we can also search with partial specification. In this partial specification, we can see that the mark type is bar, and the visualization retrieval also containing the components of bar chart. Next, I will move on to our conclusion. So first, in this work, we developed a multimodal retrieval system connecting search and authoring for genomics visualization. We compiled 3,200 interactive visualizations across categories, searchable by three modalities. And we found that simple context-free grammar method achieve efficient and accurate retrieval at low computational cost. And thank you so much for attending my talk. And these are the links to the preprint and our open source repository on GitHub. Thank you so much. Please let me know if you have any questions.
Thank you so much, Huyen. We're already a little late time-wise, but we have time for a quick question if somebody has a question. No questions, I think. So then we maybe just use that and move on because we're a little late. And I think, Huyen, you will be available online also on Juno if some questions come up, right?
Yes, of course. Thank you.